Okay, we're going to be looking at prototype number 11, Gauss's law and the electric potential. As in all my videos, whenever you are asked a question or asked to do a calculation, pause the video, try your hand at it, and then continue the video. A conducting sphere, radius 12 centimeters, is charged uniformly with a surface charge density of minus 100 nanocoulomb per meter squared. Use Gauss's law to explain why there is no electric field inside the conductor. Pause the video, write your explanation. Now let's consider the conducting sphere at radius r, and I'm going to place a Gaussian or imaginary surface on the inside of the conducting sphere. And the first question to ask yourself is, if there is a charge inside the Gaussian surface, is there an electric flux through the surface? Pause the video, answer the question. Yes, if you consider that the electric flux through a closed surface is defined as the enclosed charge over epsilon naught. Is there a force on the charge? Well, if there, consider that and answer the question. Yes. And what direction is that force? Well, the direction's going to be, since it's minus charge, the direction it will be toward the outside surface, positive R direction. Now you should be able to figure out why that is the case. Now use Gauss's law to calculate the electric field at some distance r, where r is some distance outside the conducting sphere. And we can start with the integral of E dot dA equal to Q enclosed over epsilon naught. And of course, that should be the closed integral. And we go with the enclosed charge is the surface charge density times the area, which is the surface charge density times 4 pi r squared, 4 pi r squared being the surface area of a sphere. And now we can state that the closed integral of E dot dA equal to the E times the closed integral dA, which is just E times 4 pi r squared. In this case, little r squared, which is the radius outside the surface of the conducting sphere. And I show r outside the conducting sphere in green. We can complete this integral and relate these two parts, okay, here and here, set them equal, and we find out that E, the electric field, is the surface charge density times the radius of the conducting sphere divided by epsilon naught times r squared, the radius at some distance past the surface of the sphere. Now calculate the electric field at r equals 15 centimeters. And if we do that calculation, we find out that the electric field is 9,040 newtons per coulomb, or 9.04 kilonewtons per coulomb. How is the electric potential difference related to the electric field? Now you should be able, I'm asking only for the relationship. Of course, the electric potential difference is equal to the integral minus the integral E dot dr. dr in the radial direction in this case, since we're dealing with spherical symmetry. And we can further write that as minus sigma over epsilon naught, where sigma is the surface charge density times r squared, and the integral of 1 over r squared dr. Now, what is the electric potential at the surface? Remember, there's a difference between electric potential and electric potential difference. And electric potential is the electric potential difference where we have taken a zero reference. And for this case, the zero reference is at infinity. So to do that, we're going to take minus the surface charge density over epsilon naught times r squared, the radius of the sphere, integrated from r to infinity 1 over r squared dr. And we have our answer minus sigma over epsilon naught r. And that's what it should be since I know I'm dealing with a negative charge. And we can get a numerical answer by plugging in the values is 942 kilovolts. Now show that V on the inside of the conductor is the same as that on the surface. Take a few minutes and try to work it out. Use the fact that E is equal to minus dV dx. I will end there and let you figure that last part out.